Now, on page 990, you will notice we have some talks about piecewise, smooth, connected, and simply connected. The reason I'm not getting into those fully, because they can use those terms in some definitions throughout the chapter, but there are no exceptions. Every time we do a problem, it's either piecewise or connected or simply connected. Kind of like when we say, hey, if a function is continuous, then integrate. And in first semester calculus, all the functions that we integrated were over a finite interval and were continuous. The only time you came across that exception was in second semester calculus, and that's when you learned about improper integrals, and you have to use L'Hopital and all of that stuff. So here, all the problems are going to be piecewise, smooth, or connected, or simply connected. No exception in calculus. The exception comes up in engineering. When you get there, they'll tell you how to deal with them. For now, I have this theorem, and notice what's titled. Fundamental Theorem of Line Intervals. There's only one fundamental theorem of calculus, has two parts, and there's only one fundamental theorem of line intervals. Line intervals is what we're going to use all throughout this chapter for all our engineering applications. And this is the basis, the fundamental theorem of those line intervals. Let C be a smooth curve joined by A and B in a plane or in space, it doesn't matter. And this is the parametric equation for it. Let F be differentiable and continuous, no exceptions. And suppose we know how to find the potential function. Suppose we know how to find a function f so that when we apply the gradient on this function, we get the vector field. If you are integrating the integral along C of f dot dr, do you know what that is? That's work. That's circulation. That is everything that we did up till now almost except for flux. It says this is what? This is this f evaluated at that b minus that f evaluated at that a. So this is a simple function evaluation, like y2 minus y1. Literally. What do you have to do? You have to be able to find such a function. So here they give us a problem, and here I'm going to start elaborating a bit on what they're giving us. They give you these things in the beginning without telling you what they are. Look what they're giving us. This is a side note. They're really giving us the integral of yz, xz, xy, dotted with dx, dy, dz. Do we agree that this is a vector field? And do you agree that this is dr? So you're going to be doing the same thing over and over and over, and at the end they're going to put everything together. I'm going to put everything together for you from the very beginning. So this is really the integral of f dot dr, nothing more. But what do they mean by this? What the heck is that? Well, look at the directions. It says, show that the differential form, this is by the way differential form, this is how differential equations look like, is exact. Remember, exact and conservative to us mean the same thing. Meaning what? Meaning show that the gradient of f, the gradient crossed with f, is 0. I, J, K. So I'm saving you memorizing a lot of theorems and definitions. You're welcome. And this is yz, this is xz, and this is xy. And that would be what? In the I, that is the partial with respect to y minus the partial with respect to x. The j, the partial with respect to x minus the partial with respect to z. And the k, the partial with respect to x minus the partial with respect to y. And I get this to be the zero vector, so yes, it is exact. Exact, conservative, the same thing, slightly different applications, but the same analogy. Now what? Now, they're trying to show us how to use this fundamental theorem. Then they say, okay, well, can you find this function f? Can you find f such that the gradient of f equals this vector field, and use it to evaluate those two values? So, I am going to start again by saying, well, this gradient function is really going to be f sub x, f sub y, f sub z, and that's going to equal yz, xz, and xy. Let's see how that works. If I start from the beginning, always the first term, I'm going to say f sub x equal yz. I'm undoing a partial derivative. F is going to be x, y, z plus a function of y and z. Now, even though this is a special case and I could get to the answer quickly, I'm still going to do this the long way. If I take the partial with respect to y, I will get xz plus g sub y of yz, and that should equal the xz. Those cancel out, so g sub y of yz equals 0, and when I integrate, I'll get g of yz to be some function of z. So this is some function of z, and now when I take the partial of f with respect to z, I will get xy plus h prime, and that should equal xy. And yes, that does cancel out if this is conservative or exact in this case, and those cancel out, and h prime ends up being 0, and h is a constant. So I was able to find a function f of x, y, z to be x, y, z. And by this definition, since this is exact, guess what? Now I'm going to put added things to you. The integral of f dot dr, which is the integral of yz, xz, xy dotted with dx, dy, dz, which is going to equal the integral from the point 112 to 350 of x, y, z. I'm sorry. Oh, come on. It was right there. Of 112 to 350 is going to simply equal f of 350 minus f of 112. Otherwise, I was going to repeat myself. And that would be, well, what is f of 350? Isn't that 5 times 3 times 0? That's a 0. And what is f of 112? Isn't that 1 times 1 times 2? Which is 2, and that would be a negative 2. And there it is. Instead of doing all of that work and taking the path, I can just evaluate it, end minus beginning, and that's that. On the last portion of this section, 18 through 22, although, number 18 through 22, although they are not defined on all the spaces, that's okay, associated with these exercises are conservative, find a potential function. Again, you need to read what f is. F is twice the cosine of y, 1 over y minus 2x the sine of y, and 1 over z. Otherwise, you really have to memorize all of these different forms that they have, which we don't want. So, my f is right there. That is my vector field f. And that's, of course, dr. So, for now, I need to find my function f of x, y, z, right? So, I'm going to say the partial of my function with respect to x is twice cosine of y. Integrate, f is going to equal 2x cosine of y plus a function of y and z. And no, this doesn't get old, and I'm not going to stop saying that. So, if I take a partial with respect to y of this, that is negative twice x the sine of y plus the partial with respect to y of yz. That should equal this component. That is 1 over y minus 2x the sine of y. Those cancel out. And when I integrate with respect to y, I will get g of yz equal natural log of absolute value of y with respect to y plus some function of z. So now this is slightly different. this is natural log of y plus h of z, and f equals 2x the cosine of y plus that. And now if I take a partial of this f with respect to z, that's going to be a 0 plus h prime of z, and that's going to equal the 1 over z. If you integrate, I'm getting h, that's an integral, that is an ugly integral, boy, I want this to look pretty. H of x, where did x come from? H of z is going to equal natural log of absolute value of c plus c, so this is natural log of z absolute value plus c. So I was able to find my function f of x, y, z to equal twice x cosine of y plus natural log of absolute value of y, natural log of absolute value of z plus c. And I know that this integral up there, I'm talking about this integral, is going to simply equal f of 1 pi over 2 minus f of 0 to 1 by the fundamental theorem of line integrals. That would equal 2 times 1 cosine of pi over 2 is 0 plus natural log of pi over 2 plus natural log of 2. And if I take f of, oh, I made that capital letter, my mistake, I made that to be f. F of 0 to 1 is going to be 2 times 0, that's 0 plus natural log of 2 plus natural log of 1, which is 0. So this is a natural log of 2, and this was a natural log of 2 plus natural log of pi over 2. Those cancel out. I'm left with natural log of pi over 2. And if I try the same on the last problem, this is the last problem I want to try. I'm trying to do as many examples as I can. This way, you are in very good shape as far as review. So first I want to find f such that, well, f sub x is actually, again, you don't have to start with that all the time. You can start with any of those that you want. You can start with f sub z. But if you start like this, the order turns out to be nice. If you integrate, f is going to equal x squared over 2, so the x squared natural log of y minus x, y, z plus some function of y and z. Now again, the goal is to find this, and that's why you need both of those. Take a partial with respect to x, with respect to y, and that's going to be x squared times 1 over y minus xz plus the partial with respect to y of yz, and that should equal the j component. And it turns out that this happened to be a constant. But this constant, what we meant by constant, was a function of x. And now if I use the last, that is take the partial with respect to z, that would be a 0 minus xy plus h prime, and that should equal the negative xy, and h prime of z will equal 0, so h is a constant. No problem. So basically, again, this says this is going to be f of 2, 1, 1 minus f of 1, 2, 1. Figure that out, and there it is. And there's the homework. I just saw that I had more time. I didn't pay attention to that. Well, I could figure out what f of 2, 1, 1 is. That is natural log of 1 is 0 minus 2. So that's a 2 minus, and f of 1, 2, 1. That would be a 1 natural log of 2 minus 2. Those cancel out, and I'm left with negative natural log of 2. And there it